So if we have capillary bed, the internal environment will be constituted by the interstitial fluid and the plasma, while the intracellular fluid will not be the internal environment. So, of course, the two compartments are not isolated. We do know that between them there is the plasma membrane, and we talked in our previous lecture how substances are transported across the plasma membrane through, electrochemical gradients, chemical gradients, or active transport. But mostly we're talking about osmotic activity. And so if the control of stabilization of the internal environment is what homeostasis is, what are the parameters within the internal environment that we want to keep stable? So we do have, of course, average values, a range, which is mostly observed in people, so a standard deviation. And then we do have the lethal limits. So for O2 and CO2, we have a partial pressure of 40 millimeters of mercury with, fairly wide non-lethal limit for both of them, but actually a fairly narrow physiological range. Beyond this physiological range, we have the condition that we call pathology. And this is where I'm going to start to introduce, the concept of pathology, of disease, as deviation from physiology. And physiology as what is defined by homeostasis. So levels of oxygen, for example, below 35 millimeters of mercury will be associated with hypoxia, and above with hyperoxygenation of the blood, which can be, very toxic. I don't know if any of you are scuba divers. I am a scuba diver, so you need to keep, one eye on the levels of oxygen, especially at high depths, and sometimes you have to increase the levels of nitrogen to decrease the partial pressure of oxygen if you go below a certain depth. Sodium, potassium, calcium, very important. Changes in the levels of sodium are easily lethal, and there's not much room for wiggling around. So glucose is an interesting one because we do know that glucose has this homeostatic level of 6 millimoles per liter, which is not easy to remember. It's much easier to remember 100 milligrams per 100 ml of blood. And this is an homeostatic parameter with a range between 80 and 120, or better 90, 110 milligrams per 100 milliliters of blood. And diabetes is the situation in which the homeostatic regulation of glucose is altered for, different reasons, depending on the type of diabetes. But going below the physiological level of glucose in blood will lead to hypoglycemia, and above will lead to hyperglycemia, with the consequences that you will see, in the diabetes lectures and PBLs. But the origin of that is disruption of the homeostatic mechanism that keep glucose stable. Blood pH is another very important one. So when they say that, the acidification of body fluids, of your internal environment, is associated with increased risk of cancer, so you should have sodium bicarbonate to increase, all these pseudoscience, pseudomedical claims. It's all censored, word. It's all balls. It's all balls. You can't change the pH of blood. If you change the pH of blood below 7.9 and above 8, you die. You decrease it below 7.3 and above 7.5, you will be very, very ill. So there's no way of change, and I'm not talking about being ill as cancer, I'm talking about acute toxicity and death. You see, there's not much tolerance. So if you get to drink too many alkaline solutions and saturate the ability of your kidneys to expel the bicarbonate ion, to excrete it, then you will be in trouble. And the same for acidosis. So it is very important for the blood to remain always at a very tight level. And also, there are several mechanisms, from the bicarbonate in the interstitial environment to the excretion of CO2, so breathing more frequently and more deeply, that will decrease the pH of the blood. Or via the kidneys by excreting more protons via the urine. And then finally, temperature, which is expressed here in Fahrenheit, but also in Celsius. And as you can see, every one of you knows what fever is. But besides the fever, which is an immune-mediated response, here we're talking about hypothermia and hyperthermia. As you can see here, the boundaries are even more restrictive. And we do have death above 42 degrees and below 18 degrees. So again, very restrictive conditions. So once again, the homeostasis is the control or the stabilization of the internal environment, and this changes if changes occur due to the pathological incapability of the regulatory systems to keep it stable, that leads to ill health and sometimes to death. So our brain, and the one of every mammal, needs a constant supply of oxygen and glucose. If we interrupt the supply of oxygen and glucose to the brain, like to the whole brain at the same time, that will lead to death within 30 seconds. So, it's a very restrictive parameter. And, microorganisms which have a parasitic relationship with the human body exploit these features by disturbing the internal environment. I'm not talking about those that induce fever, because as a matter of fact, fever is not an alteration of the internal environment. Fever is a physiological response to a possibly pathogenic agent which entered the internal environment. So, the recognition of pathogen-associated molecular patterns leads to non-specific immune responses, such as the fever. Hyperthermia or hypothermia is alteration, a pathological alteration of the internal environment. Fever is a perfectly physiological response. The alteration in chloride secretion into the lumen of the intestine caused by the L-tor strain of the cholera bacteria, of the Vibrio cholerae. Vibrio cholerae exists in the L-tor variant, and the L-tor variant contains this process which alters the chloride secretion in the lumen of the intestine. It stimulates chloride secretion in the lumen of the intestine, and that calls sodium in the lumen of the intestines, which calls water in the lumen of the intestine, causing copious defecation, causing explosive diarrhea. And that diarrhea, leads to the death of the host by dehydration, but it also promotes the spread of the microorganism. Another example is the buffering function of hemoglobin towards oxygen. So hemoglobin has a high affinity for O2, and it releases O2 only if there are low partial pressures of O2 in the internal environment. So, there's some sort of a self-regulating mechanism there due to the affinity of O2 for hemoglobin. And CO2 levels in the blood are mostly regulated via respiration. So when I say CO2 levels in the blood, I mean carbonic acid levels in the blood, because you know that CO2 in the blood can either be bound to hemoglobin, while the free fraction of CO2 in the blood is dissolved in the form of carbonic acid. And the excretion of CO2 via expiration, so the hyperventilation, leads to decreased levels of plasma CO2. And the release of CO2 decreases the level of carbonic acid, increasing the pH of the blood. That's why hyperventilation can lead to involuntary contraction of muscles and shaking, as it happens in panic attacks. While hypoventilation can lead to increase the plasma levels of CO2 with decreased pH of the blood. Other examples of homeostasis are the maintenance of electrolytes, which we will mostly look at when we talk about body fluids in the next lecture, and we will talk a lot during the renal lecture. Blood sugar regulation and acid-base balance, and again we will talk a lot about this in our renal physiology lecture and in the renal physiology workshop is called, the poster workshop. And then once again the blood pressure regulation, which is one of my favorites, and of course the temperature regulation. So in the case of temperature regulation, the hypothalamus contains in the brain certain neurons which receive information from the peripheral and central thermoreceptors. And the hypothalamus works pretty much like a thermostat. It receives information about the peripheral and core temperature of the body. And, if this is too high in comparison to a set value, it will promote behaviors and autonomic reactions to dissipate heat, while on the other hand, if the temperature is too low, it will trigger behaviors and autonomic reactions to maintain heat, to avoid the dissipation of it. So for this to occur, for example, in the case of the hypothalamic regulation of body temperature, we need feedback systems. These can be negative feedback systems, which are those systems in which the effector system opposes the initial stimulus. So, here I say, an increase in blood pressure causes a compensatory decrease in blood pressure, right? An increase in blood pressure leads to a decrease in peripheral arterial resistance, leading to a decrease in blood pressure. Same goes for hypothalamic regulation of temperature, right? If we're out in the sun jogging, our hypothalamus will order our sweat glands to produce and release more sweat. And the sweat on the skin will consist in water evaporating, and water evaporating will remove heat from our body. So, the effector mechanism opposes the initial stimulus, bringing the levels back to an homeostatic level. Then we do have positive feedbacks, and positive feedbacks are a bit of a contradiction when we talk about homeostasis, but they're actually, while they're fairly rare, they're actually very important for the survival of the organism and of the species. And are those systems in which the effector reinforces and or amplifies the initial stimulus, which means that if we have an initial stimulus which brings a value away from a set value, then the effector will bring that value further away from the set value. So, for example, the formation of a blood clot stimulates further clotting, and this is great if you're having an hemorrhage, because it stops the hemorrhage. It's not good if you have a blood clot forming on the wall of an artery, due, for example, to an atheromasic plaque due to the accumulation of LDL cholesterol in the wall or in the arterial wall, which leads, to chronic inflammation, the formation of a plaque, of a blood clot, and and that will lead, to a thrombus, which then can lead to an embolus. So, positive feedbacks have a physiological role, but they can also be dangerous. Another example of positive feedbacks is the production of oxytocin in producing the contraction of the myometrium, the smooth involuntary muscles of the uterus during childbirth. The contraction of the uterus leads to the production of more secretion of more oxytocin from the pineal gland, from the hypophysis, which leads to more contraction, which leads to more release of oxytocin. So, negative feedback systems account for basically all physiological regulatory mechanisms. It makes sense, yeah? Homeostasis mostly relies on negative feedbacks. Otherwise, you don't maintain the set value, right? You move away from the set value. So negative feedbacks can be, of course, very different from one another, right? The negative feedback for the regulation of blood pressure will be different from temperature, will be different for osmolarity, will be different for contribution of oxygen and CO2 in blood, and so on and so forth. But they're all characterized by 4 common features: a set point, which is the physiological parameter being regulated; sensor, so an organ or a group of cells which monitor, and it's sensitive to the variation in these parameters. So it's pretty cool, right? Our body actually contains measuring instruments. The ability to detect an error, a discrepancy between the set value and the value detected by the sensor, so a comparator. And then finally an effector, which is the organ or the system or the tissue which puts into effect the compensatory change. I will follow with the last bit of these